All right, so we're going to start into Unit 2, which is going to deal with biochemistry and chemical reactions and such on the front end. And then on the back end of this unit, we'll touch some basics of soil science, which will play into some chemical properties that we need to learn before we get into some soil science. And then that'll kind of wrap up the unit here. So some things that are probably some review for you, some vocab especially, but it's not going to hurt to go back over it. The first one is elements. So an element is a substance that is made up of only one type of atom. So for example, oxygen. Okay, so the chemical symbol for oxygen, or the oxygen that we breathe, is O2. Okay, even though it is O2, it's a molecule, but it's still made up of one element. The picture example down here is gold. Okay, the symbol for gold is AU. It's on the periodic table. It's an element. Okay, so atoms. Atoms are the basic unit of matter, and they are made up of three subatomic particles. So you have protons, electrons, and neutrons. And we need to remember what type of charge those subatomic particles carry. Okay, so protons are positively charged, and that's easy for you to remember. And how I remember it is proton starts with a P, positive starts with a P. Okay, so protons are positively charged particles. So if we look at this picture down here, it is the blue subatomic particles with the plus sign in it. Electrons are negatively charged particles. And so electrons, the E and N, they don't really relate. But if we go ahead and we jump down to neutrons, neutrons are neutral, okay, N, neutrons neutral. And neutral means that they have no charge. So if you remember what protons are, and if you remember what neutrons are, then by a simple process of elimination, you're only left with negatively charged particles, which is an electron. So electrons do have a negative charge, and they are not found in the nucleus of the atom. They orbit the nucleus of the atom. And in the nucleus, this center ball right here is only, let me get my pointer, is only protons and neutrons. So the nucleus of the atom is going to have a positive charge, and the orbitals of the atom is going to have a negative charge. And remember, opposites do attract. So this last statement, the nucleus of the atom is composed of protons and neutrons, and the electrons orbit the nucleus, much like the planets orbit the sun in our solar system. All right, so the periodic table. The periodic table is a way to organize known elements into like groups. We'll do a little bit of work in ag bio with the periodic table, but not a whole lot. But we do need to be reminded of some simple concepts that does go with the periodic table. All right, so the table lists basic information concerning each element. First one is the atomic number. Okay, typically the atomic number is going to be found in the top part of the box. Okay, sometimes upper right, upper middle, upper left. It's a number in the top part of the square on the periodic table. This is the number of protons in that particular atom. The atomic number does not change. For example, every carbon atom is going to have 6 protons. Okay, the number of protons determines the identity of the element. So for this element in this picture is chlorine. Chlorine is always going to have an atomic number of 17. Okay, that means it's always going to have 17 protons. Now, the atomic mass, or the mass number down here, can change. The amount of electrons that chlorine has can change, but the number of protons has to stay consistent in order for it to be chlorine. If we subtract 1 from the atomic number, then we're at 16, or if we add 1 to the atomic number, we're at 18, and we no longer have a chlorine atom. Okay, think of it like a fingerprint. Each atom, each element has its own fingerprint. Once that fingerprint is changed, then you're no longer dealing with that particular atom. So the mass number, or also known as the atomic mass. This is the mass of one of the atoms. This is the mass of the protons plus neutrons plus electrons. Usually the number of neutrons can be found by subtracting the atomic number from the mass number. Okay, so if we take 35.45 and subtract by 17, okay, then we're going to get close to the number of neutrons. Here's why. The mass of the electrons is very small, and it represents very little of the total mass of the atom. And a neutron's mass is slightly larger than the proton. So when we subtract, if we just took 35, if we rounded it, okay, 35 or 36, and we subtracted 17, then we would get a number. And that number would be close to the number of neutrons, but almost probably exactly the number of neutrons that are in this particular atom. Okay. Electrons carry very little mass, very little weight. A lot of times with these, you'll see a lot of decimal numbers after the decimal place. That will be typically your electron mass. So isotopes, another vocab term. Isotope is an atom of an element that has different numbers of neutrons from other atoms of that element. Isotopes differ in the number of neutrons only. The number of protons and electrons remain the same. The last part of that statement is extremely important. Okay, so if we look up here at the example, all of these are helium atoms. Okay, red will be protons. Helium has 2 protons. It has an atomic number of 2. The yellow subatomic particles are neutrons. Okay, we can change the number of neutrons. Sometimes that happens naturally. Sometimes it's it can be done scientifically or man-made wise. And this is all still helium, but the mass is different between these because we have added neutrons. And remember, neutrons are neutral, they don't have a charge. So we're not necessarily changing the identity of the atom, we're just making it larger, or we may be making it less stable. And that's where we go to here. Isotopes are sometimes unstable, which leads to radioactive decay. And when we hear radioactive decay, yes, there can be a negative consequences of this, but also this radioactive decay can be used to find out how old something is when we're talking about organic matter. So the rate of decay is constant. So these materials can be used to date organic and inorganic matter. This is known as carbon dating. Carbon dating. So if we take C14 and we know the rate at which it decays, then we could take a piece of organic matter and date how old it is based off of how much C14 has decayed. Electrons. So the number of electrons in a non-charged atom is always equal to the number of protons. And say that again. In a non-charged atom, the number of electrons always equals the number of protons. Positive and negative charges have to cancel out. Atoms on the periodic table do not have a charge in that state. So when we look at the atomic number of an atom on the periodic table, for instance, carbon, okay, carbon has an atomic number of 6. So that means that carbon has 6 protons, and in order for it to not have a charge, it has to have 6 electrons. 6 positive charges plus 6 negative charges equals an overall charge of 0, okay? Now, when we start having reactions or ion, we make ionic bonds, then we'll start getting some positively and negatively charged atoms. So valence electrons, another vocab term. These are electrons that are located on the outermost layer of the atom or the outermost orbit. Electrons travel around the nucleus at varying speeds. As the atom gains energy, the electrons will travel faster and can move further away from the nucleus. As atoms lose energy, the electrons may travel slower and move towards the nucleus. If an atom gains a particular amount of energy, it can lose its outer electrons. Keep in mind, when we talk about energy, typically we're talking about heat. Okay, as you heat something up, the electrons will move faster, and sometimes those valence electrons can kick out of the orbital the of the atom. This is how electricity works, and conductivity works. And this is how when you turn on a light switch, you get light at a light bulb. So this is what we're talking about here. So the rate of energy that the atom has will determine on where you may be able to find an electron. Now, the only problem with models like these is it has these electrons that are look nice and organized and certain orbitals. And while that helps us when we're organizing and counting electrons, that's not really factual if we were looking at an actual atom. Okay, these electrons are moving all around these orbitals. They don't stay in just the same pattern. Again, it bases all off of the amount of energy that an atom has. Last thing with valence electrons is valence electrons control how reactive an atom is. Okay, Some elements or some atoms are more reactive than others, and it's all based off how many valence electrons they have. For instance, the noble gases, okay, we're talking right here, neon, argon, so on and so forth, they're not very reactive because they have a full valence electron shell, meaning that they don't need any more electrons to be full, okay? And we'll talk about that more in depth later. So ions, an ion is an atom that has a positive or negative overall charge. A positive charge is the atom that has lost electrons. And that should make sense if you think about it, okay? If an atom loses negatively charged particles, or if an atom loses electrons, then it's going to have more positively charged particles than negatively charged particles, okay? So that's going to give it an overall positive charge. Positive ions are called cations. For an example, sodium readily loses its outermost electron and becomes a sodium ion or Na+. Okay? Sodium up here in this picture is the green element. It has one valence electron. So it's left with a choice if it wants to become full. And I use that term with quotation marks with my fingers when I say it. I know you can't see that. But the outermost shell wants to be full. All atoms want their outermost shell to be full. So for sodium, it has two options. It needs 8 in this particular shell to be full, 8 electrons. So it can either lose the one valence electron that it has or go out and find 7 more. Okay. Now, we're all very intelligent people. Which one do you think is easier? Lose 1 or find 7? Lose 1 is way easier than to find 7. So sodium is readily going to give up that one negatively charged electron, which is going to give it an overall charge of positive 1. Okay? A negative charge is when the atom gains electrons. So it's going to have more negatively charged electrons than protons. Negatively charged ions are called anions. So for an example, chlorine readily gains an electron and becomes a chlorine ion or Cl minus. So if sodium loses the electron, chlorine's ready to pick it up. If we count how many valence electrons are in the outer orbital, 1, 2, 3, 4, 5, 6, 7, okay? And remember we said it needs 8 in that particular orbital to be full, then it has two choices. It either loses 7 electrons or it gains 1. Okay. Now remember, in order to lose electrons, it has to gather energy to kick them out. That's a lot of energy to kick seven electrons out of their home, so to speak. Okay. So it's going to be a lot easier for chlorine to pick up one more electron to become full. So it will have one more, oops, let me go back, sorry, one more negatively charged particle than it does positively charged particle, which is going to give it an overall net charge of -1. Molecules and compounds. Molecules are formed when two atoms are joined together chemically. So, for example, you have oxygen and you have water. Compounds are formed when at least two different atoms are joined together chemically. Okay, an example of this is water. All compounds are molecules, but not all molecules are compounds. Okay, molecules um, have to be two of the same atom combined chemically, where compounds could be two different atoms joined together chemically. Okay, O2 is a molecule, oxygen is a molecule and a compound. No, I'm sorry, let me say that back. O2 is a molecule but not a compound. H2O, water, is a molecule and a compound. Chemical bonds. So a chemical bond is a physical phenomena of chemical substances being held together by attraction of atoms to each other through sharing, as well as exchanging of electrons or electrostatic forces. Okay, so what does that mean? Well, the valence electrons are going to cause atoms to bond in some shape, form, or fashion, whether they share those valence electrons or they give up or gain valence electrons, or they just have some type of attraction between the atoms. Chemical bonds equal stored energy. It takes energy to create bonds, which is why when you break them, energy is released from those bonds. So kinetic versus potential energy. Potential energy is stored in the chemical bonds. Okay, it has the potential to do work, but it's not doing work yet. Kinetic energy is the energy that is released when the chemical bonds are broken. That's active energy that is ready to be used. Different types of bonds have varying amount of energy, and that's based off how strong the bond is. And in order for it to make sense, and it should make sense, if you have a stronger bond, the stronger the bond, the more energy that is going to be stored, or the more potential energy that is going to be stored in that particular bond. The weaker the bond, the less potential energy will be stored in that particular bond. So the first type of bond, chemical bond, is a covalent bond. This is when two or more atoms are sharing electrons. This is the strongest type of chemical bond. So this is going to give you the most kinetic energy because it is going to store the most potential energy in the bond. Okay? Polarity is when there's an unequal sharing of electrons. This creates a positive and a negative pole on the molecule. So if we think about it, if we look at a water molecule, oxygen is bigger than the two hydrogen atoms. So oxygen is going to have more of a pull of the electrons than the hydrogen atoms, creating polarity. This is going to be important when we talk about water's properties. Water being polar is what makes water what it is. Next type of bond is an ionic bond. This is when two or more atoms are transferring electrons back and forth. This is the second strongest bond. This is formed between a positive and a negative ion. So this goes back to sodium losing an electron and chlorine picking one up. Okay, so sodium becoming +1, chlorine becoming -1. Put those together, the compound has an overall charge of 0. Compounds that are formed with this typically form crystalline structures. Okay, NaCl is known as table salt. Okay, that's the common name for sodium chloride. Okay, so you put sodium and chlorine together and you get table salt. The next type of bond is a hydrogen bond. This is a magnetic attraction between two polar molecules. It is usually between a hydrogen atom on one molecule and an oxygen or nitrogen atom on the other molecule. These bonds are the most important bonds in living system, and this goes back to polarity. Okay, this goes back to when we talked about water being polar. Water's not the only thing that can be polar, but it is the most important thing to living things that is polar. And the last one is van der Waals forces. Okay, this is a slight attraction between oppositely charged regions of larger molecules. It is important in temporary bonding between enzymes and substrates. These are the weakest of the interactions between two molecules. So enzymes and substrates deal with how cells operate, how we get material in and out of cells in order for them to do a process in both plants and animals. So when we get to Unit 3 and we start talking about cells and their function and their structures, then we will need to revisit van der Waals forces when we're talking about enzymes and substrates. Okay? All right, so I know this was a little bit longer of a video. Feel free to replay it, pause it whenever you need to, write questions, take notes, or email me if you have questions. Be sure you complete the form that goes with this, and we will see you very soon.